Previously, we have seen the simple implementation of the PLL circuit. So, that simple implementation is just to recollect, the simple implementation was with the help of a mixer, a simple low pass RC filter followed by an oscillator. Okay. This is what we saw earlier, and at the end of the last session we actually found the small signal block diagram for the simple implementation. Okay. In this session we would like to see that how these two blocks are related with the help of an example. So, this is V in, this is V out, you have R and C here, this is V error, and this is the control voltage of the oscillator. And we have seen the relationship between V error, V in, V C and all other variables. The corresponding small signal block diagram which we drew in the last session was this. You have phase error detector which takes input phi in, this is positive, this is negative, and it goes through a block whose gain is KPD followed by the loop filter which is modeled using R and C here with transfer function loop filter of S, then followed by the VCO whose transfer function is K VCO by S, and the output of this is fed back. Okay. This is phi out. Now, one is the actual implementation of the PLL, the other one is a small signal model of the PLL, or you can say a linear gain model of the PLL, as you see on the left. Now, to understand that how these things work, we will take an example. So, let us say in our example, V in is, we know, is sine of omega in times t. Initially, in this example, we will treat that the phase offset is equal to 0, okay, and the amplitude is also 1, just to simplify our calculation. And V out is 1 times sine of omega out t. Okay. Now, at time t equal to 0, I have omega in as omega and omega out as omega minus delta omega times 0. This is the frequency of the oscillator at time t equal to 0. You can also call this, let us say, as the free running frequency of the oscillator. So, as you see, at time instant t equal to 0, the input and output are not frequency matched. The KVCO here is equal to 2 pi times 100 into 10 power 6 radians per second. Okay. Normally, it can also be written as 2 pi into 100 mega radians per second. These are just the ways in which we write. Okay. So, initially there is frequency error between the input and the output frequencies. So, if I write at any given time that what is the frequency error, that will be omega in minus omega out. Okay. Now, to understand this particular block, we will do part by part. First, let us see if we only focus on the phase error detector part. So, when we only focus on the phase error detector part, what we see here is, only focus on phase error detector means you are looking at the phase error detector kind of in open loop. So, you have V in, you have V out. Okay. If this is in open loop. In PLL, it is not in open loop, but to understand that how this closed loop works, we will go part by part. So, here V error as per our yesterday's or previous session calculation is half times sine of. So, here I will choose cosine, okay, half of sine of 2 omega minus delta omega times t plus sine of delta omega t. This is what we have as V error. Okay. The phase error which we want to calculate between the input and the output, this phase error is equal to input phase, which is omega times dt, minus the output phase, which is omega times, by the way, this is delta omega of 0. We are treating this in an open loop, which means that V in and V out are fixed signals, which will be given with the frequencies as given here times dt. So, what you are going to get here is delta omega 0 times dt. So, if you treat the mixer in open loop and you have a frequency error between the input and the output signal, you are going to get the phase error given here, where one component is at 2 omega minus delta omega and the other component is delta omega 0 times t. Okay. And the phase error would linearly increase with respect to time. Okay. This is delta omega 0 t. When I have the frequency error between the input and the output signal, phase error appears to be linear, delta omega 0 times t, and the V error, if you look at, V error has two frequency components. One is 2 omega minus delta omega and other is sine of delta omega 0 t. So, if I am not controlling this in the loop, then V error will be sinusoidal in nature, okay, and your phase error will be linear in nature, right. Now, the control voltage which we have here, this control voltage is the filtered version of the error voltage. In this particular application, if I just do this, let us say I have this RC filter here, and for the RC filter this is V error and this is VC. Just treat this as standalone. If I feed this particular V error to my system and delta omega 0 happens to be much lesser than, okay, 1 over R C, which is the filter bandwidth, and 2 omega minus delta omega 0 is much greater than 1 over R C, then what you are going to see at the output of the filter, V C of t will be more or less 1 over 2 times sine of delta omega 0 t. Okay, is this a condition? So, your error output has both the frequencies 2 omega minus delta omega and delta omega 0, but your control voltage will have only one frequency standalone. Okay. Now, if this is the control voltage and you have an oscillator which is shown this block, this is your oscillator block, okay, whose output frequency, so I will just write this as a block standalone VCO, whose output frequency is given as, this is V control and we know what is V out, but the way the frequency is controlled at any given time is omega out of t is equal to omega free running plus k VCO times Vc, okay, which will then lead to omega out as omega minus delta omega 0 minus k VCO times Vc what is VC? This is given here. So, you have k VCO time by 2 into sine of delta omega 0 t. So, what you see here is that the output frequency will change if I feed in the control voltage as given here. Okay. In response to this output frequency, your phase out at any given time is going to be, you can integrate your omega out dt, and this is going to be omega minus delta omega 0 times t minus k VCO by 2 integral of sine delta omega 0 t dt. You will get the output phase like this. Okay. So, what we are doing here is we are breaking this particular PLL into into different parts, and we look at each part in an open loop. Later, we are going to close the loop and see what happens in the closed loop. This is important to understand what is happening at each node. So, we have seen with the phase error detector, we have seen with the loop filter, and then we have seen with the output phase. Okay. So, for the output, given this output phase, if I just consider for this particular output phase, our phase error at any given time is going to be phi in of t minus phi out of t. What was phi in of t? Phi in of t was omega times t, and phi out of t is omega minus delta omega 0 times t plus k VCO by 2 times integral of sine of delta omega 0 t dt. You may ask a question that how can this will remain at delta omega 0 all the time? Well, it will not remain at delta omega 0 all the time. This is just in the beginning. When you are closing the loop, that is the frequency error. As when the loop is open, as you close the loop, the argument of this will keep on changing, but we are just trying to understand that what happens in each case. So, here what you will see is that this is delta omega 0 times t plus k VCO by 2 into sine of delta omega 0 times t dt. So, you see that the phase error in response to the phase accumulated by the VCO, the phase error has two terms, which one is linear and other is an integral of the sine wave, right, which will be periodic in nature. Now, I told each of these things in open loop, and when I close the loop, I will see some kind of response which I am going to show you here. So, what I do here is I plot phase error by 2 pi. So, let me just write it. I plot here phase error at any given time divided by 2 pi for different cases, and I also plot V error and other voltages. So, let us look one by one. So, in this case, the phase error increases linearly with time, which is delta omega 0. So, the curve which you see is this, the blue one. Okay. When I highlight, this is the curve which is increasing linearly with time, and I am plotting phase error by 2 pi. So, what you see is that the output value is 1 in place of being 2 pi or 3 pi, so on. Then the next one is your error voltage or control voltage, which you see here, this one, sine of half of sine of delta omega 0 t. So, I plot that in the bottom figure, and you see that this error voltage is actually sinusoidal in nature. I am removing this particular component because I know that this component is going to be filtered off by the loop filter. So, that is the blue component. Then in response to that control voltage, I change the frequency, and when I change the frequency, I get the phase error which is shown this particular phase error. In response to the control change in the control voltage as per the phase error, you get a new phase error which is shown here. It has a linear term, it has sinusoidal term. So, then I again plotted this phase error term, and what you see is something like this. It is periodic in nature. Okay. So, I will just do it like this. This is periodic in nature. So, you have a linear component and you have this component. Okay. All these things were in open loop, and in response to this phase error, now you are going to have your error voltage, that V error of t happens to be half of sine of phase error of t, right. So, this is half of sine of phase error of t. So, in response to the phase error which is periodic in nature as shown here, I again plotted the error voltage which is shown by the green curve. Okay. So, all the things which I am plotting, right, with respect to time, they are like treating different blocks of the PLL in parts. When I close this loop, when you think about it, when you have a frequency error, you get voltage error. This voltage error changes the control voltage, which is going to change the omega out again error, and it is in negative feedback. So, finally, it will try to reach the case where your omega out is equal to omega in. Okay. And that is going to happen when omega out will be equal to omega in. When will this happen? When you see this frequency relationship here. So, this is equal to omega minus delta omega plus k VCO times Vc is equal to omega. Okay. So, what you see is control voltage should be equal to delta omega by k VCO. When you reach this control voltage, you will recover you will compensate for the frequency error initially. And what was this control voltage? This particular control voltage was half the sine of the phase error. Okay. So, phase error is going to be 2 times delta omega by k VCO, and this whole thing will come inside the sine argument. So, that your phase error is equal to sine inverse of 2 omega by delta omega. Okay. So, you see that two things settle here in closed loop. The one thing which settles here is, you see that it comes from here and it settles at some value, and for phase V error also, you see that this settles in some time. So, this is the closed loop, the red curve which you are seeing, they are in the closed loop simulations. So, what you can find from here is that once you reach the control voltage which compensates for the frequency error, right, you will also at the same time you will also have certain phase error which is non-zero in this particular stage. And to verify simply, you can think about it that initially the example here which I chose was that your omega was actually, in this case, omega was 50 2 pi into 50 mega radians per second. Okay. Delta omega 0, this was equal to 2 pi into 5 mega radians per second. Okay. So, if that is the case, the values which I have chosen, initial analysis is for any value. Finally, the example which I plotted here, there the delta omega 0 was 5. Delta omega 0 here was 2 pi into 40 mega radians per second, okay, and omega was 2 pi into 50 mega radians per second. So, based on our frequency error, what you have is 2 pi into 40 mega radians per second by kVcu, which was 2 pi into 100 mega radians per second per volt. So, you see this voltage is 0.4 volt, okay, and that is where your error voltage settles to, which is 0.4 volts. Okay. Now, this particular phase error happens to be the sine inverse. You can calculate with respect to this value, and you will find that is equal to phase error by 2 pi is 0.1476. Okay. Here kVcu is sorry, here this is kVcu 2 pi into 100 into 10 power 6 radians per second per volt, this mega radian per second per volt. Okay. So, now what we understand from this particular analysis is that our PLL given the frequency error, how the PLL logs, how the waveforms at different parts of this simulation will look like. Okay, different parts of this PLL block diagram, how will they look here. Okay.